Gas pressure also has a big effect on our weather. Variation in atmospheric pressure causes wind, and changes in the pressure help us to predict the weather. So here's a weather map where we see a low pressure region and a high pressure region, and meteorologists study these different regions, and that allows them to predict what the weather's going to do. I mean, think about it, wind, right? I mean, we know what wind is. Why is wind? Well, yeah, heat rises, and so we've got warm air rising and cool air falling, and pressure differences come up. So when we have a high pressure system, that's usually associated with clear weather, and a low pressure system is associated with unstable weather. We have a little weather station up here, and it shows the atmospheric pressure, and it also gives these little picture predictions of what's going to happen, whether it's going to be stable, unstable, etc. And the way it does that is by looking at, is the pressure going up or going down? So the number of gas particles in a given volume of air is also dependent on the altitude. How far away from sea level are you? As we go higher and higher into the atmosphere, into the mountains, up in an airplane, the gas pressure, the atmospheric pressure decreases. That's why in an airplane they have, it's pressurized so that we can breathe, because otherwise at the height that an airplane flies, there's not enough air and people would pass out, which would not be desirable. That also happens, you go up into the mountains and you thought you were in pretty good shape, but you go hiking and you're just out of breath so quickly, because there is literally not as much oxygen in the air, and so you need to breathe more in order to get enough oxygen. So the pressure of the atmosphere varies with the weather, but it also always varies with changes in altitude. Here we have a picture, two mason jars with gases in them, a lower pressure and a higher pressure. A higher concentration is associated with higher pressure. A lower concentration of the gas is associated with a lower pressure. And when we think about collisions with the sides of the container, that should make sense, because here we have fewer particles. They're not going to collide as frequently as in this container where there are more particles. Sometimes I think of gas particles as being a bit like kindergarten children. And so here we have two classrooms, and this one has a lot more children in the same size classroom. And if the teacher steps out for a minute and the kids do what kids do when there's no adult around, they start going wild, right? They just start running around. These children are going to run into each other and literally bounce off the walls more frequently than the children in this classroom, where there's just not as many in the same volume. Does that make sense? So fewer gas particles means lower force per unit area and a lower pressure. Pressure imbalances also explain the popping sensation we get in our ears when you're flying. As you go up and down, you get this popping sensation, or if you drive up the hill to Grant Grove, your ears will pop on the way up and on the way down. Inside your ear, there's an eardrum that separates your middle and outer ear from your inner ear. And there is air on each side of this eardrum. The pressure is the same on each side, but if you go up in elevation quickly, then the external pressure decreases, the internal pressure stays the same, and that causes your eardrum to bulge outward. And that can be mildly uncomfortable, or if you have an ear infection, it can be horribly painful. And that's why babies tend to scream on airplanes, is because their ears hurt. Because they're eustachian tubes, which is this little tube here, which is how the air inside your your inner ear can equalize in pressure. This tube is connected down into the back of your throat. If you have a cold or upper respiratory infection where things are kind of swollen, then it's more difficult for that eustachian tube to open up and allow the pressure to equalize. And in young children, their eustachian tubes are smaller, and so it's also much more difficult for them to equalize the pressure. So what happens as you go up, when the pressure inside gets high enough then it will release through the eustachian tube and you'll have a sensation of popping. As you come back down into higher pressure, your ear has equalized to the lower pressure, and now the outside pressure is greater, and so your eardrum's going to bulge the other way again until the pressure can equalize. Anybody have any questions? I just think it's always interesting when chemistry explains things that we experience every day. How do we measure pressure? Well, we have some very fancy types of devices to measure pressure, but we're going to talk about the original pressure measurement device, the Mercury Barometer. It's a very simple device. We take a long glass tube, fill it with mercury, invert it into an open dish of mercury. If this was water, the water would stay all the way up in the top of this unless your tube was like 32 feet tall. Haven't seen one of those. But because mercury is 13.6 times more dense than water, the mercury will not retain a column as high as water would. So if this column here is 30 inches or more, what we'll see is that, if the tube is 30 inches, we'll see a vacuum form here as some of the mercury comes out of the tube. And we might wonder, well, why doesn't all the mercury run out, right? When you tip a cup upside down, doesn't water run out of it? The thing here is that the ends of the cup, the end of the tube, is under the surface of the mercury. And so the mercury is trying to go down because it's being pulled by gravity, but the atmospheric pressure is also pushing on this pool of mercury, and in order for this mercury inside the tube to come out, that would cause the level of the mercury outside to go up, which is pushing against the atmospheric pressure. So we have a balance between gravity and atmospheric pressure, and that's what supports this column of mercury. At sea level, this column will on average be 760 millimeters tall, or 29.92 inches tall. A column of water would be about 31 feet tall, and so you may have played with water and cups in the bathtub or the kitchen sink, and if you put a cup underwater and tip it upside down and lift it up, as long as the rim of the cup is still under the surface of the water stays in the cup, right? And then you pull it up and then it all runs out. And it's the same idea, but we just don't see the vacuum forming. So Torricelli is the guy who first figured this one out, and so we've named one of the units after him, the torr. So the atmospheric pressure can be measured with a ruler, just measuring how tall is this column of mercury. What he found is if he took this thing, which that must have been quite a trip because this would be heavy and kind of unstable. If you take this and you walk up a mountain, the column gets shorter and shorter as you go up. And then as you come down, it gets bigger and bigger. And when you get down to where you were before, it's the same height. Because when the pressure outside, the atmospheric pressure is lower, then the height of the column of mercury is less. When the pressure is greater, the column of mercury is taller. So higher pressure, higher column, just measure it with a ruler. Zero technology. So that's where we get this very weird sounding unit, a millimeter of mercury. How can a length of an element measure pressure of a gas, right? Seems a little silly, but it's from the Mercury Barometer. So we can measure pressure in millimeters of mercury. Millimeter of mercury is also known as a torr, two names for exactly the same thing. There are lots of other units, and we have different units because they're useful in different situations. And these pressure units are very different in size. Down here we have an atmosphere, and over here we're listing in these different units the average air pressure at sea level. So an atmosphere at sea level is 1 atmosphere, is kind of defined as that, 1 atmosphere. If we look at heights of columns of mercury, inches of mercury, because you could use an English ruler to measure that instead of a metric, you get 29.92 inches of mercury. In millimeters or torr, it would be 760. And this number is exact because it was defined that way. An atmosphere is exactly 760 torr. 14.7 psi, that's the unit that you use when you're trying to fill up your car or your bike tires. It means pounds per square inch. Force divided by area, literally pressure, pounds per square inch. And then we have pascals. This is the SI unit. It's a Newton per square meter, abbreviated PA. And this unit is very, very small. So 101,325 pascals is equal to 1 atmosphere. The way these units are set up, all of these values are equal to each other. So 1 atmosphere equals this many pascals. 14.7 psi is equal to 29.92 inches of mercury. So when we convert pressure units, it's always one step. You don't have to go through the list. It's always just one step, which is nice. Most of these we will not use very much. Like pascals, there might be a couple of questions that are just unit conversion issues where I would either give you that relationship or you could look it up if it was a homework problem. I don't expect you to memorize that. The only one that I think would be useful, let's get on to this next problem. I'll give most of these, if not all of them, to you on an exam. This top line I think is helpful to remember because it saves you time. I'll still give you the conversion though. An atmosphere is 760 torr, which is 760 millimeters of mercury. These others will be given to you. So we should be able to convert pressure units. This one says your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert this pressure to PSI. We can do this in one step. It's dimensional analysis. We have inches of mercury. We want PSI. One step. Because in this list, all of these things are equal to each other. And so here we have 14.7 psi is equal to 29.92 inches of mercury. So 30.44 inches of mercury times in a line psi on top, inches of mercury on the bottom. I look at my relationships. 14.7 psi is equal to 29.92 inches of mercury. The inches cancel out. And my calculator gives me 14.955 and a bunch of other stuff. PSI. My starting number here had 4 sig figs, and this is 4 sig figs, but this one is only 3. And so that's going to limit my answer. And when I round this, I'm going to get 15.0 psi. Yeah?
Since it's a conversion factor, aren't they considered exact numbers?
They're not considered exact numbers unless they're defined. So pounds per square inch, the relationship between pounds and the metric system is not exact. It bothers me a little bit that they give only 3 sig figs per psi because obviously we know that there's more, and it's actually 14.69. I don't know why they rounded it, but those are not exact. The only one that's exact is the atmosphere torr millimeters of mercury, because it's defined that way. Any other questions? So the barometer is used to measure atmospheric pressure. The manometer is used to measure pressure inside of a container. And it's a similar idea using mercury again. So here we have a U-shaped tube with some mercury in it. One end of the tube is connected to the container where we're measuring the pressure. the other is open to the atmosphere. And so we have the atmosphere pushing down on this side, and we have the gas inside the container pushing down on that side. The higher pressure is going to push down farther, and so here the pressure in this container is higher than atmospheric pressure, and we see that that's true because it's pushing this down. It's pushing this side down farther than the atmospheric pressure is pushing down. If this tube was open to the atmosphere, what would happen to the levels of mercury? They'd be the same on each side, right? Because gravity pulls it down, it's going to be equal. It's higher on this side and lower on this side because this gas is pushing it down. So we can again use a ruler and measure the difference between this column of mercury and this column of mercury in length. And that gives us the difference in pressure between inside the container and outside the container. Here the pressure inside is higher because it's pushing down farther. So we have to know what atmospheric pressure is and recognize the difference here, and then we can add that difference to find the pressure inside the container. It's also possible that your container might have a low pressure, and so then the column of mercury would be lower on the atmospheric side and higher on the container side. And then you would subtract that difference from the atmospheric pressure to get the pressure inside the container. Any questions? Yeah.
It's a comment. Have you seen those coffee makers that use this? They're like not with mercury, obviously, but they use like the pressure to like it looks like it's going. The coffee is like getting sucked up.
I haven't seen those.
And they kind of like teeter because there's a little heater under it, so they teeter. So like
I haven't.
to look up if you ever want.
That sounds interesting.
It's like a tower.
You might be interested in our oxalate extraction thing. We do it in our tech class with coffee, and so you can see it, and it'll run through there. Yeah.
Could you use the same principle to measure, like this, to measure the atmospheric pressure? If you knew how many moles of the molecule were inside of the container and the volume of the container?
Yeah. If you were able to calculate the pressure in here, you could.
Without the pressure, I'm saying, like, if you didn't know the pressure on the inside of it, you knew everything that was inside of it, and you knew the volume of what was inside of it, could you calculate the pressure, the atmospheric pressure outside of it?
Well, you could, but the way that you could do that is if you knew the volume and the temperature and the number of moles of gas in here, you could calculate the pressure in this container, and then measuring the difference would allow you to calculate the pressure outside. Yeah. But usually we don't have that information. Now these, of course, are very, very rudimentary pressure measuring devices, and we have much fancier things now. Like this little weather station here. These things aren't very expensive at all, but this is measuring atmospheric pressure, and obviously it doesn't have a tall column of mercury in it. We use piezoelectric devices and other semiconductors. There's all kinds of cool ways to measure pressure.